At 9:42 on Monday morning, the primary database began responding slowly. It was not offline. A storage operation briefly pushed query latency from 40 milliseconds to 4 seconds. 30 seconds later, the storage problem ended and the database was healthy again. But the application did not recover. API latency kept rising. Connection pools stayed full. Queue depth doubled every minute, and instances that had survived the original slowdown began restarting. By the time engineers understood what was happening, a tiny dependency failure had become a system-wide retry storm. The database was no longer the cause. Millions of well-intentioned retries were now the outage. This is the story of how distributed systems amplify partial failure, why exponential backoff is only one part of the answer, and how to design retries that cannot take your own backend down. This SystemSignal visual breakdown follows the incident from the first slow query to the final recovery. We will model the normal request path, watch retries multiply across service boundaries, and then rebuild the control flow with bounded attempts, jitter, retry budgets, circuit breakers, load shedding, and idempotent writes. The goal is not to eliminate retries. Temporary failures are normal, and a carefully placed retry can hide them from a user. The goal is to prevent retries from creating more work than the recovering system can complete. That requires coordination across clients, gateways, services, queues, and databases. It also requires metrics that separate original traffic from repeated traffic, because a system can appear busy while doing almost no new work. By the end, you will have a practical review checklist for any backend that calls another backend. The dangerous number is not the retry count in one function. It is the product of retry policies across the complete call chain. Imagine a mobile client making 3 attempts. The gateway performs 3 attempts for each client call. The order service then performs 3 database attempts. One user action can now create 27 database operations before queues or background workers are counted. Teams often configure these policies independently. A client library ships with a default retry. The service mesh adds another. An SDK retries throttled requests. Application code wraps the call in one more loop. Each local decision looks reasonable, but the system has no shared retry budget. During normal operation, the multiplication is invisible because the first attempt usually succeeds. During a slowdown, all layers activate at once. The traffic graph rises precisely when useful capacity falls, producing the opposite of graceful degradation. Under healthy conditions, the architecture looks straightforward. A client sends one request to the gateway. The gateway routes it to the order service. The service acquires a database connection, executes a query, and returns the result. Latency is far below every timeout, so none of the retry policies activate. Connection pools recycle quickly, and dashboards show a stable relationship between incoming requests and completed database operations. This is why retry risk is easy to miss in design reviews. Static architecture diagrams show components and arrows, but they rarely show attempt counts, deadlines, or who owns cancellation. The same arrow might represent 1 attempt or 9. A useful system design must annotate every remote call with its timeout, maximum attempts, backoff, jitter, retriable error set, and total deadline. Without those details, the diagram describes connectivity but not failure behavior. When the database slowed down, callers reached their timeouts before the original queries finished. They assumed failure and started new attempts, but cancellation did not reliably stop the work already running in the database. The original query and its replacement now competed for the same connections. Gateway retries increased service traffic, while mobile clients repeated requests they had not received answers for. Queue consumers returned failed messages for immediate redelivery. The connection pool became a waiting room filled with duplicate work. Even after storage latency returned to normal, the database faced a wall of old and new attempts. Successful responses could not drain the backlog faster than retries replenished it. Autoscaling added application instances, but every new instance opened more database connections and created more retry capacity. The system had crossed from dependency failure into positive feedback. More failure created more load, and more load created more failure. The difference between resilience and amplification is control. An unsafe policy treats every failure as permission to try again. A safe policy asks whether another attempt still has time to succeed, whether the operation is safe to repeat, whether the dependency is accepting retry traffic, and whether the system has remaining retry budget. Retries should be concentrated at one deliberate boundary, rather than copied into every layer. Each attempt must fit within the original request deadline. Exponential backoff increases delay between attempts, while random jitter prevents thousands of callers from waking on the same schedule. A retry budget limits repeated traffic to a small fraction of successful original traffic. When that budget is exhausted, the system fails fast instead of borrowing unlimited capacity from the future. Recovery is the critical moment. The dependency must receive a controlled ramp of useful work, not every delayed attempt at once. Exponential backoff is necessary, but it is not sufficient. If 10,000 requests fail together and all wait exactly 1 second, they retry together 1 second later. The traffic spike has only moved. Full jitter chooses a random delay between 0 and the current backoff ceiling, distributing attempts across time. A total deadline prevents a service from starting a retry that cannot finish before the caller gives up. Attempt limits must apply across the call chain, not reset inside every SDK. A retry budget can be expressed as a percentage of original traffic or as tokens replenished by successful requests. Server signals, such as retry after, should override aggressive client guesses. Finally, retry only errors that are plausibly temporary. Validation failures, authorization failures, and deterministic conflicts usually become worse when repeated. Subscribe to SystemSignal for clear explanations of complex engineering problems and the production details hidden behind simple architecture arrows. A resilient request path decides whether work should enter before consuming the scarce dependency. Admission control checks the remaining deadline and current capacity. The first request attempt does not spend retry budget because it represents new work. If a temporary failure occurs, the caller must reserve permission for another attempt. The circuit breaker watches a rolling window of failures and latency. When the dependency is clearly unhealthy, it opens and rejects calls locally, allowing connection pools and database workers to recover. A limited number of probe requests enter the half-open state to test recovery without releasing the entire backlog. Requests that can tolerate stale data take a cache or fallback path. Less important work is shed with an explicit response rather than waiting until every resource is exhausted. The architecture, therefore, has two success modes: a fresh result when capacity is healthy, and a deliberate degraded result when protection is more valuable than completeness. Retries are especially dangerous for writes. If a payment request times out after the server commits, the client cannot tell whether nothing happened or the response was merely lost. Repeating the request without an idempotency contract may charge the customer twice. The client should generate one idempotency key for the logical operation and reuse it across every attempt. The service stores that key, operation state, and final response in the same transactional boundary as the business change. A duplicate request returns the previously recorded result instead of performing the write again. The retention period must cover the realistic retry window, and payload mismatches using the same key should be rejected. Idempotency also extends beyond the API. Events emitted by the write need stable identifiers, and consumers need deduplication or naturally idempotent state transitions. A retry policy without a duplicate handling design is incomplete, even when transport behavior is perfect. Moving work to a queue changes where retry pressure accumulates, but it does not make the pressure disappear. Immediate redelivery can create a tight loop, in which the same failing message consumes a worker thousands of times. A poison message may block useful work, and a recovered dependency may be hit by the entire delayed backlog. Consumers should attach attempt count, first seen time, and next eligible time to the message. Delay queues or scheduled delivery, spread retries without keeping worker threads asleep. After a bounded number of attempts, the message moves to a dead letter destination with enough context to investigate and replay safely. Consumer concurrency should follow downstream health rather than queue depth alone. Scaling workers, because the queue is growing, can overload the dependency that caused the queue to grow. A production dashboard must show original messages, redeliveries, age, dead letters, and completion rates separately. During the incident, engineers first stopped the feedback loop. They disabled retries at the gateway, reduced consumer concurrency, and opened the database circuit breaker. Error rates briefly increased because the system failed fast, but connection pools began draining and useful throughput returned. Recovery traffic was then reintroduced through canaries instead of releasing the full backlog. The decisive dashboard separated original requests from attempts. It showed amplification ratio, retry budget consumption, remaining deadline, circuit state, connection pool wait time, queue age, and completed useful operations. Ordinary request rate had hidden the problem because attempts looked like demand. The post-incident change made every service emit an attempt number and a stable operation identifier. Alerts now trigger when retry traffic grows faster than original traffic, or when success requires multiple attempts for too long. Reliability improved because the system could see the feedback loop before customers could. The database slowdown lasted 30 seconds, but the retry storm lasted for hours because the application created a feedback loop it could not see or limit. The lesson is not that retries are bad. The lesson is that retries consume capacity and therefore require the same design discipline as any other workload. Give one layer ownership. Bound the total attempts. Carry a deadline through the complete call chain. Combine exponential backoff with full jitter. Spend repeated traffic from a retry budget. Use circuit breakers and load shedding to create room for recovery. Schedule queue redelivery and isolate poison messages. Protect every write with an idempotency contract. Measure original operations separately from attempts and watch amplification before ordinary request metrics become alarming. The strongest backend is not the one that retries forever. It is the one that knows when another attempt is useful, when degraded service is safer, and when stopping work is the fastest path to recovery. If you enjoy clear explanations of complex engineering problems and important developments in technology, subscribe to SystemSignal. We publish a new visual breakdown every week.